Have you ever stopped to wonder what gives our world its everything? Why is water wet and not, say, gassy at room temperature? Why does a strand of DNA twist into that perfect helix? The answers to these massive questions actually start at a scale so small it's almost impossible to imagine. So let's dive in and explore the hidden architecture that shapes literally everything around us, the world of molecules.
Just take a look at this. It's a bee orchid, and it has evolved to look and even smell exactly like a female bee. It's this incredible sneaky trick to lure in male bees so they'll pollinate it. This is a perfect example of a fundamental rule in nature. Shape defines function. And this rule, it isn't just for things we can see. It's actually even more important down at that invisible molecular level.
All right, so to really get a handle on molecular shape, we have to start with the most basic question. What holds the tiny building blocks, the atoms, together in the first place? You can think of these forces as the universe's most powerful superglues. In chemistry, we call them intramolecular bonds.
Now, this superglue basically comes in two main flavors. On one hand, you've got ionic bonding. This is a straight-up give and take. One atom gives an electron away, another one grabs it. This makes one atom positive and the other negative. And, opposites attract. Then, on the other hand, you've got covalent bonding. This is all about teamwork. It's about sharing. Two atoms share a pair of electrons, and that shared pair acts like a rope, holding them both together.
And then there's a third kind of special type of superglue that's just for metals. It's called metallic bonding, and it's more like a whole community of atoms. See, the outer electrons don't really belong to any one atom. Instead, they form this free-flowing sea of electrons that moves among all the positive ions. And that is exactly why metals are so good at conducting electricity. Those electrons can just zip right through the whole structure.
Okay, so superglue holds atoms together to make molecules. Got it. But then what makes those whole molecules stick to each other, to form a liquid or a solid? For that, we need a totally different kind of force, something a lot more like chemical Velcro.
And this little comparison really gets to the heart of it. Our superglues, those are the intramolecular bonds, like covalent bonds. They're incredibly strong. They're what hold the atoms inside a single molecule together. But the Velcros, the intermolecular forces, they're way, way weaker. They're the attractions between different molecules, pulling them together to make up all the stuff you can actually see and touch.
So here's the thing. Not all Velcro is made equal. The absolute strongest type is something called a hydrogen bond. This happens when a hydrogen atom is already bonded to a really electron-greedy atom. Think oxygen, nitrogen, or fluorine. That greedy atom tugs the electrons closer, which leaves the hydrogen with a slight positive charge. And that slightly positive hydrogen is then super attracted to a pair of electrons on a neighboring molecule. It is the king of all the Velcro forces.
And if you want to see the effect this has, just look at this chart. Water and methane are molecules that are about the same size. But methane boils at a ridiculously cold minus 161.5 degrees Celsius. Water, on the other hand, boils at 100 degrees. Why the enormous difference? It's all because of those powerful hydrogen bonds. They act like super sticky Velcro between water molecules, and you need a ton of energy, a ton of heat, to rip them apart.
So, we've covered the glues and the Velcros. We know how atoms build molecules, and we know how molecules stick together. But we're still missing the most important piece of the puzzle. There's this one elegant secret rule that decides their actual 3D shape.
So let's just ask the question straight up. How does a molecule like water or methane know what shape it's supposed to be? It's definitely not random. There's a really fundamental principle at work here.
And the answer is so simple, so elegant, it's almost unbelievable. All the pairs of electrons in the outer shell of an atom, they just repel each other. They're all negatively charged, right? So they naturally just push each other away to get as far apart as they possibly can. That's it. That's the whole secret.
This is probably my favorite way to picture this. Imagine you tie a few balloons together right at their knots. What happens? They automatically push each other away and arrange themselves to take up the most space. Electron pairs do the exact same thing around an atom.
Now, this beautifully simple idea does have a fancy name, VSEPR theory. It stands for valence shell electron pair repulsion. It's just a powerful model that lets us predict the 3D shape of tons of molecules, based on that one simple rule: keep the electrons away from each other.
And when you apply this rule, you get these really predictable shapes. If you have two groups of electrons, like two balloons, they're going to make a straight line, a 180-degree angle. Three groups will form a flat triangle at 120 degrees apart.
And four groups? They form a perfect 3D pyramid shape, a tetrahedron, with angles of 109.5 degrees.
But, and this is where it gets really interesting, not all of those electron pairs are actually in a bond. Some of them are just hanging out. They're called lone pairs. Now, when we look at a molecule's shape, we can't see these lone pairs, but they are absolutely there taking up space and pushing on everything else. In fact, they push even harder than the pairs in bonds do.
So check out what happens. Let's start with that four-group arrangement, the tetrahedron. If all four are bonding pairs, you get a perfect tetrahedral shape. But swap one of those for a lone pair, its extra pushing power shoves the other three bonds down into a pyramid shape. And if you have two lone pairs, they push the last two bonds even closer together, creating what we call a bent shape.
Let's see this in action. It makes it so much clearer. Here's methane. It's got 4 bonding pairs, 0 lone pairs. So it's a perfect tetrahedron. But now look at water. It also has 4 electron pairs total around the oxygen, but 2 are in bonds and 2 are lone pairs. Those 2 powerful lone pairs just squeeze the hydrogen bonds together, giving water its famous bent shape. So they both start from the same basic 4-part setup, but those invisible lone pairs completely change water's final shape.
So why do we care so much? Why does any of this matter? Because that bent shape, it isn't just a piece of trivia. It is pretty much the reason life as we know it can even exist. Let's connect this simple rule of repulsion back to the real world.
See, because the water molecule is bent, the electrons aren't spread out evenly. The big oxygen atom hogs them, giving its side of the molecule a slight negative charge. That leaves the hydrogen end with a slight positive charge. If water were a straight line, these charges would just cancel each other out. But because it's bent, the molecule has a positive side and a negative side. We call this imbalance polarity.
And this single fact kicks off an incredible chain reaction. That simple rule of electron repulsion forces water into a bent shape. That bent shape makes the molecule polar. That polarity allows water molecules to form those super strong hydrogen bonds we talked about earlier. And those hydrogen bonds are responsible for basically all of water's amazing, life-giving properties. Why it stays liquid, why it can dissolve so many things, even why ice floats.
So in the end, it all comes down to this one simple truth. A molecule's architecture is its destiny. The shape of a molecule, which is determined by a simple rule about electrons pushing each other away, dictates everything about it. From the stickiness of water to how a medicine works in your body, shape is everything. I mean, it's just an incredible thought, isn't it? This whole universe of complex structures and functions, and it all boils down to a simple tendency for electrons to just get out of each other's way. It really makes you wonder, what other profound, elegant secrets are hiding right there in plain sight, just waiting for us to notice?